So it is my pleasure to introduce Emanuel Guariglia from the University of Venzukin. I'm not sure if it is a correct pronunciation. So Emanuel, after this starting not so amazing, you have the floor. Please, you can start. You have more or less 25 minutes. Please.
Okay. So thank you. Thanks for the nice introduction. So in this talk, we will see some remarks of fractional calculus, the case of zeta function, and at the end we will see my recent my new research interest in Sobolev space, Sard space. It seems that this fractional derivative works well with function with function space, which is a surprise for me as well. So let's see something. Let's start and let's see some remark that all of you know what. Almost all of you should know what is the Riemann zeta function, but for reason of completeness, we see the definition here. And in the same slide, I show to you the definition of fractional derivative. This is the Grunwald-Letnikov derivative. This is the fractional derivative that best fit with this complex function. Now, in this talk, I will not discuss about the problems that currently have with the definition of fractional derivative. However, my results, I obtained the same results using almost all the fractional derivative that currently have. Why this is the best definition of fractional derivative for this problem? Because this definition satisfies a generalization of the Leibniz rule, and this helps us a lot, especially in terms of functional equation. So using this definition is very easy. Here we have a binomial series. We can get the alpha order fractional derivative of the Riemann zeta function. Okay, so one problem when we go to use the generalization of the Leibniz rule is that the generalization of Leibniz rule give us a functional equation, and we have a triple summation. This problem can be avoided using an apostole already proposed by Apostol and Spira for the integer derivative of the Riemann zeta function. That is, we work a little bit with the complex exponential. This is what Apostol and Spira did in 60 and 70 years. In the same way, we can prove that there is also an equivalent of the symmetric, because the Riemann zeta function has a symmetric functional equation, and the same holds for the fractional derivative. So T of alpha is, let's say, is almost equal to T of alpha 1 minus S, where this is T alpha of S. But here we have a double summation, and this symbol means that this is true up to a multiplicative constant. This multiplicative constant is an exponential that involves alpha. Okay, so I also proved these results in 2021. These same results can be generalized to generalization of the Riemann zeta function, i.e. Dirichlet series, Harvey series, Lerch zeta function, and so on. Here now, so the point is how we can work with this fractional derivative and use this for a class of zeta function. Well, we can treat the case of the Lerch zeta function. Lerch zeta function somehow generalize several zeta function. So again, this is the generalization. This is function that for many of you know, you had a class of special function. And using the same technique, i.e. the Grunwald technical derivative, even if the first time I use the Caputo derivative. So if you use the Caputo derivative, you have to close an integral that generally is an Euler gamma. While if you use this Grunwald technical derivative, you use with binomial series, so you get this result. And well, this is just a sketch of the proof. We don't stay here because we have just 25 minutes. So the Grunwald technical derivative of L is this limit. We can interchange here sum and limit. We don't have problem. We have a uniform convergence. And at the end, in the last right-hand side, we have a binomial series. Okay, so we can finish this way. Here, if you want to get a functional equation, we also have problem of computational cost. We can again work as in the case as proposed by Apostol and Spira. We have here just one summation, and these results come directly from the Rademacher formula of the zeta function. Well, basically, we have this. This is what. This is how this is the Apostol technique. Okay, so the Apostol technique first you have to manipulate a little bit L, and the second we must introduce an auxiliary function psi of L. In the case of the Riemann zeta function, we have a psi of zeta. Okay, so it's easy. At the end, we have that L is written as the sum of these two functions with different parameters, and so the fractional derivative of L will be the fractional derivative of these two conjugates. There is a way to link this fractional derivative with prime numbers. The first theorem here is the classical expansion of the Dirichlet series in terms of Euler product. For Fn equal to 1, we have the case of the Riemann zeta function. And this is the classical infinite sum that generally mathematicians know about the Riemann zeta function. But the problem is that this is true when f is completely multiplicative. What's happened when this is not completely multiplicative? Well, this is a problem that actually I solved. And the point is that here we can write this product, this sum as a product, but the sum inside doesn't converge. Moreover, we can compute the fraction log derivative of zeta. And regarding the critical strip, if we introduce the Dirichlet function, we remember that the Dirichlet function converges when r of s is greater than 0. So, since the Riemann zeta function converges for r of s greater than 1, the critical strip is fixed by the convergence domain of these two functions. Likewise, the fractional derivative of eta converge when r of s is greater than alpha. So it seems that their fractional derivative give us a strip alpha 1 plus alpha. Okay, so basically we have this. So this fractional critical strip shift, there is a shift according to alpha. In the same way, we can fix zero collision. This technique depends. No, this is a technique like head and tail, and was proposed for the first time in 2020. Okay, so here how we get the so we see this for the Harvey zeta function. So how does it work? First, we take the n term of the series tree, and this so the point is to find the dominant term. Okay, so the term for which here q of capital N is greater than the rest. Okay, So basically, what we want to solve, we want to solve that Q of n is equal to Q of n plus 1. For sure, these terms depend on A because the Harvey zeta function depend on A. So in the case of Riemann zeta function, this we will have that this term here is Q alpha n 1. So the solution is this Q, and that's quite easy. That's quite easy. Okay. So now what we will have that the Harvey zeta function has no zero in this wedge Q n a alpha plus b1, and the right hand side is Q n minus 1 a alpha plus b2. So how we fix b1 and b2? b1 and b2 are fixed when we find the dominant term. And the dominant term is, we get the dominant term using this equation that we saw before. Okay, so now we arrive to the main point. So we split our term in head, H, and tail. Okay, so that's quite easy. So we split this. Why we split it this way? Because the term n equal to n, small n equal to capital N is our dominant term. Okay, so our main aim is to find this. Okay, so if we find this, okay, we get that zeta alpha as A doesn't vanish. Okay, so I found this zero free region in 2023. Currently, I will work now in another direction that I explain you now. So we have for sigma greater than Q2A alpha plus 3.2, we have that the Harvey zeta function is not zero. So this is a zero free region. And for sure, this works for all A such that the Harvey zeta function exists. Okay, so after I will show you the references. So this has some corollary. For instance, for every d greater than 0, there exists a gamma real such that if sigma is greater than gamma, so we have a zero free region. And this other theorem where we find some domain where zeta alpha SA, so our Harvey zeta function has just 1 0. So this is not for a zero free region. So, for instance, that's a plot. So here, the wedge we see here in green, in yellow, and in dark blue are our zero free region, and this corresponds to this second theorem here, and better than better to this definition here for sigma. Okay. Now my research will move on function space. Why? Because if we come back here, we see that this fractional derivative, why it's so special? Because it's equal to the integer derivative of Riemann zeta function. Just we have to replace alpha with n, where n is the integer order of differentiation. So this means that probably we can, for instance, we could define a function space that has this property. Moreover, we can study this function in the fractional Sobolev space WSP. These nowadays in fractional calculus, these are are well-known spaces. The same for the Hardy space and fractional repression operation, for the regularity, and so on. Okay, so these are my references. You find the main results you saw in the first and second paper. If you want the definition of Grumman electrical derivative to the complex plane, see this paper of Trujillo, or maybe better, the last paper of Lee, Dow, and Guo for fractional derivative in complex space. and you find some results of the fractional derivative of the Arvin zeta function. The first paper, while the link with primes is discussed in this paper published in Advanced in Difference Equation. Last two papers show the techniques used by Apostol and Spira, especially this paper of 85. If you go in this paper, you find also a lot of details about the zero-free region. Thank you.
Thank you, Emanuel, for the presentation. Any question?
So, any question? Okay, any question?
Thank you for the nice talk. I have a question concerning a paper by Bruce Berndt, 2 years after Spira's result. He proved that that the number of zeros of the kth derivative of the Riemann zeta function was related to up to height t in a rectangle, complex rectangle with height t, is related to the number of zeros of the Riemann zeta function plus a factor which depends on t. Do you have a similar result for fractional derivative?
No, because the fractional derivative of this function, as far as I know, was discussed a long time ago, little bit, and after I wrote my PhD thesis on this topic, and there was also another scholar that wrote his dissertation after me, Ferran Hernandez. And so now people seems that there are some new interest, but in 60, 70 years, nobody dealt with this topic. So we have some topics, we have some results which are very, very similar, like could be the critical strip, the functional equation, and maybe now we can, I am confident that I can do something that I can do something with function space. But there are other topics which are totally different, and this depends on the difficulties that we currently have in fractional calculus. And we have a lot of difficulties in fractional calculus. Thank you for your question.
And another question. There are some some error terms for the number of zeros of the kth derivative of the Riemann zeta function, which depend on the Riemann hypothesis, some very strong whole terms like log t over log t. Do you have analogous also for, do we have some conditional results on the Riemann hypothesis in your results?
The point is that we should formulate my opinion is that we should formulate a sort of fractional Riemann hypothesis, and we should prove that under some condition the fractional Riemann hypothesis converges to the classic Riemann hypothesis. So if we do this, your question makes sense, and these results are of great interest. If we don't formulate, if I don't, or if scholars will not formulate a fractional Riemann hypothesis, we cannot do this.
Okay.
But this new strip that is function of alpha maybe will allow us to formulate a fractional Riemann hypothesis.
Okay. Nice. Thank you.
Thank you. Thank you.
Excuse me, one more question. Perhaps you have some, do you have some criterion of equivalence for the Riemann hypothesis involving fractional derivatives?
No, as far as I know, there are not this criteria. I want to, so You mean for a general definition of fractional derivative or for this fractional derivative?
This kind or any another type of fractional derivative involving zeta?
No, as far as I know, there are no criteria that involve, because as I told before, my hope is that we find a fractional Riemann hypothesis.
Okay.
And we should prove that under some conditions, the fractional Riemann hypothesis converges to the Riemann hypothesis we know. And this would be a very nice result. So thank you for your question.
But kind of if and only if you don't have, no?
No, we don't have.
Okay, thank you.
You're welcome.
Are there any other comments or questions? No, thank you, Emanuel. We thank also all speakers of this session, of both sessions of this morning. So thank you also here, all the participants in our room. Let's close the session, I think. Organizers, can we close the session? Yes, we can. Thank you.
Thank you. Bye, bye, bye.